Hello students, welcome to JCE Connect. This is lecture 6 of module 1, and in today's lecture, before starting off with the actual content, let us quickly have a brief recap of what we discussed in our previous lectures. Right? So we discussed about the well-posed learning problems, the designing learning systems, right? Various uh, choices for training experience or target functions, right? And the approximation functions, and also the perspectives and the issues in machine learning, right? So here we are going to discuss about the concepts learning and the general to specific ordering, wherein in the previous lecture we learned about our concept learning tasks and also the introduction part, right? So today's lecture, the focus will be on the concepts learning as such and general to specific ordering for hypothesis. Right. So without wasting much time, let's quickly jump into what we are going to learn. So this is what we have learned in our previous lectures. We discussed about the representation of hypothesis, the attributes, these things, taking the example of uh, the enjoy sport, right? So starting off with the concepts learning as a search, wherein we'll be discussing about the general to specific ordering of hypothesis. Now, getting more into depth that what is a concept learning as a search, right? What it provides, what it can be viewed as, right? So the concept learning, as you can see, is can be viewed as a task of searching through a large space, right? It can be viewed as a task of searching through a large space. This space is of hypothesis. Now, this this task of searching through the large space of hypothesis is defined by the hypothesis representation. Right now, the main goal of this whole search is to find the hypothesis that best fits into the training example. Right? The let me on the writing pen here. Yeah. So the main goal here is to search for the best fit for the training example. Right. So just for the example, what we have talked about in our previous lecture, using the same example, that is the enjoy sport, the instance X and the hypothesis H in that particular enjoy sport. This can be the concept learning for the search, right? The instances X and the hypothesis H. Now, it is important that it is important to note that this selecting a hypothesis representation, the the designer of this whole learning algorithm defines the space of all the hypotheses, right? It defines the space. We'll discuss what this space is all about, uh, but the designer of this particular learning algorithm has to define the space of all the hypotheses that the program can represent, right? So let us have an example. Like let us to understand that. Let's say that the attributes, as you can recall from the table that we discussed. Let me quickly go back to those tables. The table which is shown right here, right? The table 2.1. You can see there are different parameters that we have and different values, right? So let's say, for example, the attributes. These attributes, the sky, air temperature, humidity, wind, water, forecast, and ultimately the target function, that is the enjoy sport. So let us assume uh, this that the attribute sky has three possible values, right? And the air temperature, humidity, wind, water, as well as the forecast, they all have two possible values. So then the the instances space X, right? The instance space X, we'll discuss what this space is. will contain exactly 3 into 2 into 2 into 2 into 2. That is the dot product of all the possible values of all 6 parameters. Right? We have 6 parameters here, what we discussed in the table. So if you can remember, the first parameter was the sky, second air temperature, humidity, wind, water, and the forecast. So assuming that sky has 3 possible values and all the other has 2 possible values, then the dot product will give us 96 distinct instances, right? It will give us 96 distinct instances. Now, having said that, let's have a similar calculation. Let's say there are around these many 5.4.4.4.4. That is, dot product comes to around 5120. We have, let's say we have 5120 syntactically distinct hypotheses within the set of hypothesis H, right? So this hypothesis containing one or more these symbol, which is 5, right? Which is the symbol that represents the empty set, right? Empty set of instances or no value is permitted, right? So it classifies every instance as negative. Now, the value with this symbol classifies those instances as negative. Therefore, the number of syntactical distinct hypotheses, the total number of syntactically distinct hypotheses comes down to this value, right? Which is the dot product of all the values reduced and like all the values minus one, and ultimately getting the total number of semantically distinct hypotheses at 973, right? So note here that we are we are having syntactically distinct hypothesis as 5120, and when we have symbol representation of 5 for all the which is classified, which classifies every instance as negative, then we have semantically distinct hypothesis as 973. So the example, that is the enjoy sport example, is actually a very simple learning task, as you can clearly make out. It is very simple when it is given to a human, right? So, but for the machine, it might be a little challenging task, right? So though our example, this enjoy sport example, is a very simple learning task, with a relatively small and finite hypothesis space we had, very relatively small and finite hypothesis space. But most of the practical or real-time learning tasks, they involve much larger and at the same time sometimes infinite hypothesis spaces. So that is the difference. So having said that, let us move forward and understand the general to specific ordering of these hypotheses. Right. So as the name suggests, as the title suggests, that the general to specific ordering of the hypothesis is what we are going to see how it can be computed. How can we make a general hypothesis to a very specific hypothesis? So here you can see that uh, we have considered the set of instances, right? Uh, let's say instances are H1 and H2, but the algorithm, the many of the algorithm for this kind of concept learning organize this particular search through the hypothesis, like we have discussed in the previous lectures, right? How? By relying on a you know very useful structure like what we discussed in the previous slides, in the previous lectures, right? Relying on a very specific, very useful structure. Now this structure, let's say this general to specific ordering, let's say it's a very uh, useful structure that exists for any concepts learning problem. Now, by taking advantage of this, by taking advantage of this useful structure, we can design learning algorithms that you know uh, that search even infinite hypotheses. For the for our previous example, that is enjoy sport example, which had very finite hypothesis, very finite hypothesis, right? And a smaller hypothesis space, you can say. But this can be used, this structure can be used to design more uh, advanced and infinite hypothesis spaces without explicitly enumerating every possible hypothesis. Now, to illustrate this, we have this H1 and H2, hypothesis 1 and hypothesis 2. So, these two hypotheses, let us consider these. Let us consider the set of instances that are classified as positive. Okay? Let's consider these uh, instances as a positive by H1 and by H2 both. Now, because H2 imposes fewer constraints, you can see here we have only one constraint in H2, and H1 we have two constraints. By constraint, I mean because I say this constraint because we are giving a specific value that this a particular hypothesis, like H1, should have first attribute as sunny and fourth attribute as strong. But when we see hypothesis H2, we are only giving one constraint, that is the first attribute has to be sunny. Others are question mark. That means they are uh, don't care conditions, you can say, or we are not bothered about any specific value there. So, having said that, that fewer constraints we have here, we can clearly say that H2 imposes fewer constraints on the instance, and it classifies more instance as positive. And any instance classified positive by H1 will also be classified by H2. I hope you all agree to it. Like, if any instance which is classified as positive by H1 itself, it can be positive by the H2 also, because H1 has more constraint, H2 has lesser constraints. So, in a nutshell, we can say that H2 is a more generalized format. You can say H2 is a more general hypothesis than H1, right? So H2 is more general than H1. Now, by more general, this brings us to the to a relation that is more general than. The relation is called the more general than relationship. Now, this more general than relationship between these hypotheses can be defined, more precisely with these points, as I mentioned numerically. So, let's say at first, let's say for any instance x, we have any instance x in a set of instances capital X, and the hypothesis H in set of hypothesis X. We say that the instance X satisfies the hypothesis if and only if Hx is equal to 1. H of x is equal to 1. Right? So it is quite evident that like for any instance x in capital X, and any hypothesis H in capital H, the X will satisfy H if and only if the H of X will be 1 or positive. 1 denotes here positive. Right? So, having said that, we now have to define the more, general than or equal to, more general than or equal to relationship. Now, this more general than or equal to relationship in terms of a set of instances that satisfies the previous two hypotheses. Uh, what we have showed in the previous slide. Right? Let's say given hypothesis is Hj and Hk. Okay, let's say we have two hypotheses Hj and Hk. So Hj is more general than or equal to Hk only if, let's assume that Hj is more general than or equal to Hk if and only if any instance, that is X, satisfies Hk and also satisfies Hj. Right? I hope you agree to this. Right? To give a better definition, let me demonstrate this. Let Hj and Hk be a Boolean value function, right? Let needs to be a Boolean value function defined over capital X. Now, then the Hj is more general than or equal to, we can say that Hj is more general than or equal to Hk, and which is written as this format. Hj is greater than or equal to is more general than or equal to Hk if and only if we have this statement, right? Now this is, you know, it, let's say, let me wipe this off and do it again. Right? Yeah. So the Hj is more general than or equal to Hk if and only if for all the instances x, for all the instances x belonging to capital X, that is the set of all instances, and h of k is equal to 1, hk of x is equal to 1, which also implies that hj of x is equal to 1, right? Because hk is more specific and hj is more general, right? So hj is more general than or equal to hk, which can be written like this if and only if this condition implies, right? So moving ahead, that uh, we will also have to find it we will also find that useful that to consider cases where one hypothesis is strictly more general, right? We looked upon condition where we saw more general than, and then more general than or equal to, but let us uh, consider this case wherein one hypothesis is strictly strictly more general than or the other, right? Strictly more general than the other. So we can say that the hypothesis is strictly more general than other. Let's say hypothesis Hj is strictly more general than Hk, which is represented by this formula here. This format, you can say Hj is more general than Hk if and only if we satisfy this condition, right? If and only if we satisfy this condition. This is what that Hj is more general than Hk, and now this is the logical conjunction and or a logical and operator. So both the values here, both the parameters here has to be true, right? Only then this condition will be true. So we can say that Hj is strictly more general than Hk if and only if Hj is more general or equal to Hk. Also, this and Hk is not more general than Hj, right? Hk is not more general than or equal to Hj. So this is the logical and operator here. That means both the condition has to be true. Now, having said that, the final final part, we can say that the finally we will have another case wherein we may find we will sometimes find the inverse of these conditions as useful ones, depending on the learning problem, depending on the situations, right? So we will sometimes find the inverse also can come handy. Now this inverse will let's say let's say that Hj hypothesis Hj is more specific than Hk when Hk is more general than Hj, right? So simple fact. Hj can be more specific than Hk when Hk is more general than Hj. Simple, right? So one important, aspect to be focused here is let me demonstrate this with an example by the space, the instance space, right? So let's say we have this diagram. We have few set of instances x, and we also have set of hypotheses denoted by capital H. Now, consider these three hypotheses that we have. We have H1, right? I'll have a small tick mark here. We have H2 and we have H3. So we have these three hypotheses here, and you can see that the box on the left represents the set of all instances, and this box on the right denotes the set of all the hypotheses denoted by capital H. So each hypothesis, which is corresponds to some subset of X, right? The subset of instances that is classified as positive. Now each hypothesis, you can see here, each hypothesis corresponds to some subset of X. H1 is corresponds to this subset, H2 is corresponds to this whole subset, and H3 will corresponds to this subset. Right? Let me point out a laser here. Yeah. So this is H1, this is H2, and this here we have is H3. Right. So the arrows here in this right box, the set of hypotheses that we have, the arrows connecting the hypothesis here. Let me point out with the pen. Yeah. So hypothesis, this arrows here connecting the hypothesis, they represent that it is more general than the relationship. For example, H2 is more general than H1. H2 is also more general than H3, which can be easily, you can view it here in the instance space, wherein you can see H2 is a bigger space, so it is more general. H1 is smaller, H3 is smaller than comparatively H2. Right. So that means that H2 is more general than H1, and also H2 is more general than H3. So these arrows plays very important role. We have to focus more on arrows. Right. So these instances are more specific, right? And these instances below, we can say they are more general comparatively. So with the arrows pointing towards the less general hypothesis, now please note here that the subset of instances characterized by H2, right? The subset of instances characterized by H2. Let me draw this. That talking about this subset. This subsumes the subset categorized by H1 and H3, right? H1 is this, and H3 is this, right? So H2 subsumes the subset categorized by the H1 and H2, H1 and H3, pardon, right? So hence we can say that the H2 is more general than H1, and H2 is also more general than H3. Now one more thing to be noted here is that neither H1 and nor H3, that is this and this. Let me point out with a laser. Yeah. Now this and this, right? They neither H1 and H3 is more general than the other, right? So these neither set uh, subsumes the other, right? They themselves don't subsumes the other, right? There is one instance here which is not in instance of H1, and there is one instance in H1 which is not in H3, right? So having said that, likewise we can have the concept learning algorithms. Uh, one such example is the finders algorithm. So we'll discuss about those finders algorithm in the next lecture. So, but these concept learning algorithm, like let's say finders algorithm, they take the advantage of this partial order, the partial ordering, because we can say this partial because we are only working on a few sub instances, right? So now the algorithms like finders algorithm can take the advantage of this partial ordering to efficiently organize the search for the hypothesis, right? To efficiently organize the search for this hypothesis. Why? Because that that can fit the training data, the hypothesis that can fit the training data. So let me conclude here. If you have any kind of doubt or anything, you can post it in the comment section, and or you can reach me out in the our WhatsApp group or at our Google Classroom also. Right. So all the platforms are available to you. If you have any kinds of doubt, you can feel free to ask, and if anybody else having similar doubts, they may also get clarified. Right. So in the next lecture, we will discuss about an algorithm which deals with what we learned today. That is the find S algorithm, which is a kind of a concept learning algorithm. Right. So thank you, and whatever that we have discussed in today's lecture, please note down in a particular notebook whatever the important points you feel. If you feel any any more clarification on particular uh, point that we discussed, you can ask me anytime. Right. So thank you, and stay tuned for the next coming up lectures.